So hello everyone, welcome to my talk. I want to first thank the organizer for inviting me here to share my work with you guys. So my name is Lu. I'm currently a postdoc at UC Berkeley. But the talk I'm gonna present today is meaning about the work that was done when I was a postdoc at the University of Sherbrooke in the group of Professor Louis Taillefer. So the topic of my talk today is gonna be thermal Hall effect in quantum materials. So I put it this way because it's gonna be like a tutorial type of talk, which including the following part. So first of all, I'm going to give, this is the outline of my talk today. So first of all, I'm going to give a very general introduction about what is a thermal Hall effect measurement and how do we actually perform the measurement in experiment, okay? And after that, I'm going to talk about the thermal Hall effect that has been done in different types of material and starting with the thermal Hall effect in metals, which is maybe people think like the most trivial case. And then I'm going to move to talk about the thermal Hall effect in insulating materials, which is more like the focus of this workshop this time, which is about the neutral type of excitations like phonons, magnons, and how can they give you a thermal Hall effect. And after that, I'm going to go a little bit deeper to talk about a new way of doing a thermal Hall effect measurement, which is the so-called planar thermal Hall effect in different types of quantum materials. So before I give my talk, I would like to first give the acknowledgement. I want to thank all the members from Professor Louis Taillefer's group for all of their great contribution and help for the thermal Hall work that we have been done in the past. And also the rest of them, they are our collaborators for providing us with a very nice samples that has been measured in this thermal Hall type of research. So, okay, so let's first take a look what is a thermal Hall effect measurement and how do we perform the experiment in reality. So the figure here shows the schematic of our measurement setup. So usually for this type of so-called thermal transport measurement, we will have a very thin plate-shaped like sample, like rectangular, and you glue one end of the sample on a heat sink, which is usually made by either copper or lithium fluoride, some non-magnetic materials. And then on the other end of the sample, you put a heater here. So the heater can be used to generate a thermal gradient along the sample. So the thermal gradient along the x direction can be measured usually by two thermometers, which is the so-called T plus and T minus here. And with this so-called delta Tx, you can use that to calculate the longitudinal thermal conductivity. Okay. So, but in a material that actually has a non-zero thermal Hall effect, so what will happen when you try to apply a magnetic field perpendicular to the sample plane is you will get a non-zero transverse temperature gradient, which is the so-called delta Ty here. Okay. So this figure clearly shows us that the thermal Hall effect just looks like the thermal analog of an electrical Hall effect. So for electrical Hall, you give it the electric current, you put the field, you get a transverse voltage difference. But for thermal Hall, you put a heat current, and in the presence of a field, you get a thermal gradient transversely. Okay. And with this setup, we were able to measure both thermal conductivity and thermal Hall conductivity simultaneously. Okay. So one thing is I need to emphasize is for these types of thermal Hall effect measurement, usually the net signal you can get along the transverse direction, which is delta Ty, is about 1,000 times smaller than the signal you can get along the longitudinal direction, which means generally, if you have a delta Tx about several Kelvin, your delta Ty is about several millikelvin to tens of millikelvin. So this means it's a pretty hard experiment to perform, and you need extremely high temperature stability for your system. And the last thing to put into context, so in reality, there are multiple sources like excitation that can carry entropy or carry heat, and that can also give you a thermal Hall effect in the presence of the magnetic field. For example, like electrons, which is a charged carrier, and then like some neutral type of carrier like magnons, phonons, and Mariana fermions. So I'm gonna cover them one by one in today's tutorial talk. So here is the actual image under the microscope for our thermal Hall type of measurement setup. So you can see the whole picture here. The big chunk of yellowish color stuff is our measurement probe made by copper. And then on top of that, we put all the measurement component. For example, in the middle of the figure is where we put our sample here. So here I just use one of the cuprine material, YBCO, as an example. So we'll put the sample on heat sink material and put it in the middle of the probe. And then surrounding the sample, you have all the other components like thermometers, heaters, which you can use to measure the thermal Hall signal directly. For example, the things on the left-hand side and on the right-hand side, they are basically components you can use to measure temperature difference. For example, you can either use a thermometer like Cernox, ruthenium oxide, or you can use something called a thermocouple. They can all do this job for you. And on the far end of the sample, you can see which is circled by the blue circle here, where this is the sample heater. So all these measurement components, they were thermally linked to your sample to help to detect all the temperature differences or to send in the heat. Okay. So this is the measurement setup. And then here is a picture about exactly where we put this measurement probe inside. So for the type of system that we conduct our thermal transport measurement is usually we use something called a variable temperature insert system, which is a cryostat, goes from 1.5K to 300K, and then it usually equipped with a very strong magnet because we need a very strong field to actually distinguish a lot of the thermal Hall effect in the material that we try to study. And you put a probe inside the VTI and then apply field. And you also use other different types of electronics to help you read the signal. So this is just in general how the whole measurement setup looks like. So now let's talk about the first type of families of materials, which is the thermal Hall effect in metals. So let's start with something more simple. And one thing is, so if you measure whatever, like thermal transport, either thermal conductivity or thermal Hall conductivity in a material, the total contribution are usually come from all different types of excitations, like electrons, phonons, magnons, and everything. But usually for metals, the signals, they are dominated by electronic signals. So electrons can give you a thermal Hall effect in the same way. I mean, the most naive thinking is in the same way of electrons give you an electrical Hall effect. Because when the electron propagate inside a magnetic field, because of the Lorentz force, they can give you a Hall effect. So electrical Hall and thermal Hall, they are corresponding to each other. So this is exactly what one thing I'm going to show you guys here is basically the thermal Hall effect measured in oxygen-free copper, which is one of the most simple type of metal materials. So you can see what has been plotted here is the thermal Hall conductivity kappa xy versus the magnetic field. And you see in copper, it already has a very large thermal Hall effect along all these different temperature ranges. And one thing for metals is what we know is something called the Wiedemann-Franz law. So Wiedemann-Franz law tells us that we can always use the electrical Hall conductivity to estimate how much the electrons can contribute to the thermal Hall effect. So basically, this formula tells us the thermal Hall conductivity divided by the electrical Hall conductivity, this should be equal to some constant. So the figure on the right-hand side, exactly the blue curve is the electrical Hall conductivity estimation that coming in sodium, which is another elemental type of metal. And then the red curve is the actual thermal Hall effect that has been measured in this material. Okay, so this is just the regular metals, but actually the thermal Hall effect, the first time people think it's super important or useful is to measure other metallic type of material, which is a superconducting material. So here I'm just use YBCO as example. So one thing I need to mention is, so for measuring superconducting material, once it goes below the superconducting transition temperature, all the electrons form Cooper pairs. So if you measure electrical transport, so you just get 0, right? But in this case, people think, okay, we need to find some other type of transport measurement to know the quasi-particle behavior. That's how we use the thermal Hall effect to study the so-called high-temperature superconductors. So I give you one example, which is this picture. The left-hand side figure shows the thermal Hall conductivity versus field that has been measured in this YBCO, which is a high-temperature cuprate superconductors. So for this YBCO at this particular doping, so you can see the TC is around 60 to 70K, and the figure in the middle is basically the thermal conductivity versus temperature. So for this kind of cuprate materials, once the temperature goes below TC, electrons form Cooper pairs. So Cooper pairs, they do not carry heat. They don't carry entropy. However, for this particular type of cuprates, there's the so-called D-wave superconductors, which means you will have a special type of quasi-particles called D-wave quasi-particles can still carry heat for you inside the superconducting state. This is exactly how this thermal conductivity and thermal Hall conductivity, you still see the very big signal when the temperature is below TC. So what happens here is you see the thermal conductivity and also the thermal Hall conductivity, they were dramatically increased when the temperature goes below TC. Is because of the effect that below TC, electrons form Cooper pairs, which means electron-electron scattering becomes smaller, which greatly increases the so-called mean free path of the electron, which is what I plotted for you guys on the right-hand side. So this strong increase in the mean free path of electrons gave you all this strong signal coming from both thermal conductivity and thermal Hall conductivity. So the conclusion here is about 20 years ago, people found the thermal Hall effect is a very powerful technique that can be used to detect D-wave quasi-particles which live deep inside the superconducting state. And apart from that, people can directly start or go from the thermal Hall effect data to estimate the mean free path for the D-wave quasi-particles in these cuprate materials. And apart from cuprates, actually, these same types of measurement has also been performed in other unconventional superconductors. For example, like cerium, cobalt, indium 5. And on the left-hand side, what I still plotted for you guys is the big figure is the thermal Hall conductivity versus temperature taken in this material. And the inside figure is thermal conductivity versus temperature. So you can see the behavior of this heavy fermion material is very similar to what people already found in cuprates. Okay, so after that, I mean, that was what happened like 20 or 25 years ago. It's like people only use it to study metallic samples. But in the recent like 5 to 10 years, people found, okay, thermal Hall effect become extremely important or become more and more popular is because we can also use it to study insulating materials. For example, like those neutral quasi-particles that goes inside. Because for electrical transport, you cannot do anything with insulating materials. So now let's take a look at this formula again. So in an insulating material, you can ignore about the electron contributions. But what has been left is what we call a neutral excitations. For example, one type of the most well-known neutral excitation, they are magnons. So they are linked to, it's like the excitations linked to spin degrees of freedom or long-range magnetic ordering in the system. So one thing is, yes, magnons can give you a non-zero thermal Hall effect. I think in previous talk, Carlo already shows this result, which is one of the most famous example for a magnon thermal Hall effect, which has been observed, I think it's from Professor Tokura's group in this insulating collinear ferromagnetic paracoloid material, lutetium vanadase. So here, I want to see is the reason why this result is extremely convincing that people know it's from magnon is because this material, it goes into the ferromagnetic order state below about 70 K. So you see that when the temperature is higher than this magnetic transition, the thermal Hall effect is 0. And it only starts to grow to be non-zero when it goes into the order state. So this is the very first example for the thermal Hall effect coming from actually magnons in a ferromagnetic system. And the one possible theoretical explanation regarding to these types of magnon thermal Hall effect is this so-called Berry curvature coming from the DM interaction in this particular system. And also the paper that I cite here, I think Carlo also talked about this morning, is basically developed by Nagosa and Patrick, which they call them a no-go theorem. Means like in what types of antiferromagnetic system can you get a non-zero thermal Hall effect or not for magnons? Okay, and the one to keep you guys, put you guys into context, I think in today's talk, like Emily, she's gonna talk about another intrinsic mechanism that can give you a magnon Hall effect, in particular in multi-insulators. So she's gonna talk more about that part in the following part. And apart from this lutetium vanadase paracoloid materials, so there are other types of materials or systems can also give you a magnon Hall effect. So usually this kind of magnon Hall effect can come from this kind of non-coplanar magnetic moment like structure. For example, like this very famous germion system. I think this is a work from Professor Yamashita's group, Minoru Yamashita's group. So basically the general idea is when you have a magnon system or like the spin-related thermal Hall effect, basically if you have like a non-trivial topology, either in the K space or in the real space, they can all give you a thermal Hall effect. And I think in today's session, Professor Shizahota, she's going to talk about more about the theoretical part relating to the higher rank gauge fields that magnons or spin excitation can give you a thermal Hall effect. Okay, and apart from magnons, you also have phonons, but I'm going to leave phonon to the last part of my talk. So what about other types of neutral excitations? The answer is yes. For example, the very recent years, there's one very famous like material that people believe that maybe you can detect Majorana fermions that you also use this thermal Hall effect measurement. So this is related to a particular type of material, which is a so-called Kitaev spin liquid candidate. So for the Kitaev model, it is basically based on this honeycomb type of lattice relating to this bond-dependent ice interactions between spin 1/2 degrees of freedom. So the reason why this Kitaev model is so important and generated a lot of experimental motivation for the thermal transport study is because theorists had predicted if you have a Kitaev spin liquid, and it's an exactly solvable model, and they also predict that if you have Kitaev spin liquid, you will have some mobile Majorana fermions which act like edge states that can carry heat that give you a thermal Hall effect. And what is more important is this thermal Hall effect has a special type of feature, which means it's the half quantized thermal Hall conductivity has an exact value. So this theoretical prediction has triggered a lot of search in experiments to look for this kind of signal. So one of the most famous example is probably a lot of the audience here already know is the half quantized thermal Hall conductivity that has been reported by Professor Yuji Masuda's group in Japan. So back in 2018, they measured one of the most well-known K-type spin liquid candidate, which is so-called alpha ruthenium trichloride. And what has been plotted here is the thermal Hall conductivity versus field taken at different temperature. So you can see that the thermal Hall conductivity here indeed shows some plateau-like behavior, which they believe are actually coming from those Majorana fermions, which are acting like smoking gun for the K-type spin liquid. However, later on, there were other groups try to repeat this kind of result, but they saw something slightly different. So in the figure in the middle is the result come from Professor Huang's group in Princeton. They also tried to measure the thermal Hall effect in the alpha ruthenium trichloride. So they saw a non-zero thermal Hall effect, but there's no obvious half quantization in this signal. And their theoretical explanation is not based on Majorana fermions, but instead are based on something called chiral magnons or topological magnons, especially tied to this K-type Heisenberg model. And later on, like our group at Sherbrooke, we also measure the same system. But what I plotted for you guys here is thermal conductivity and thermal Hall conductivity versus temperature. If you compare these two curves, you will see their temperature dependency exactly looks like the same. So one thing about the alpha ruthenium trichloride is the thermal conductivity we already know they are contributed by phonons, which is another neutral type of excitations, which indicates the thermal Hall conductivity probably have the same origin, which is also phonon. Okay, so here comes to, before I talk about phonon, let's talk about the other things. So what are other types of neutral excitation that can also probably give you a thermal Hall effect? The answer is yes. So back in 2015, Professor Huang's group, they reported this non-zero thermal Hall effect in a perchlor oxide. And back then, they believed this non-zero thermal Hall effect coming from some neutral spin excitations, maybe like spinons in these perchlor materials. But later on, there were other group in Japan. They tried to actually repeat this type of measurement, but in this kind of substituted perchlor system. But their conclusion was slightly different. They more intend to believe the signal was actually generated by phonons instead of magnons. So for this neutral type of excitations, you will always see there are a lot of controversial interpretations within the community. And at this point, I'm going to move on to the last type of neutral excitations that can possibly give you a thermal Hall effect, which are the so-called phonons. So for phonon thermal Hall effect, I think it's just very recent 5 to 10 years, it's become like a hotter and hotter topic. So the very first observation of thermal Hall effect coming from phonon was actually done back in 2005 in a paramagnetic insulator material, which is called terbium garnet. But back then, this signal was the signal itself is very small, and people only observed it in not many different types of materials. So we start to think about, okay, maybe the phonon thermal Hall effect is something very rare, But after that, very recently, there were different groups reporting the thermal Hall effect coming from phonons in a growing list of materials. For example, in 2017, this is Professor Tokura's group, they reported it in the phonon thermal Hall effect coming from some ferromagnetic insulating materials. And the kind of mechanism they proposed is the coupling between phonon to the magnons or the spin lattice coupling. So, and after that, so our group, we observed that, okay, if you can even have a phonon type of thermal Hall effect in some more trivial type of antiferromagnetic insulator, which is called copper telluride. So the general idea is that what I want to show guys here is basically a phonon thermal Hall effect has been observed in more and more different types of quantum materials. For example, in these cuprate molten insulators, and also in some non-magnetic materials like strontium titanate and even black phosphorus. Okay, so for the phonon thermal Hall effect, the other very important example is the phonon thermal Hall effect that people detected in cuprate superconductors, in particular related to the so-called pseudogap phase. So this is also the result reported by Louis' group in Sherbrooke. So basically what we did is we tried to measure the thermal Hall effect in a cuprate type of material at 2 different doping levels. So you can see here, I want to remind you guys for the particular type of cuprate material we started is called neodymium LRCO is a whole-doped cuprates. And from the phase diagram, you can see the pseudogap phase, very mysterious one. They kind of end at a critical doping called P star, about 23%. So what we did is we found that the pseudogap phase itself actually has a new type of feature, which is a non-zero phonon thermal Hall effect. So how do we do that? Is we basically measure something called a C-axis thermal Hall conductivity. So as I show you guys in the introduction part, it's like you always need to put a field and a field direction, current direction along some certain principal axis for your material, right? And here, for the C-axis thermal Hall conductivity measurement, how we do that is we try to apply the heat perpendicular to the copper oxide plane. So one thing about cuprates is a highly 2D material, which means all the electrons or even magnons, they were highly confined inside the 2D copper oxide plane. So this means if you want to apply the heat perpendicular to this plane, there was only one type of carriers that are left can carry heat for you, which are the so-called phonons. And then what we did is we tried to measure this C-axis thermal Hall conductivity, which is a direct measurement of the phonon thermal Hall effect itself. And what we found is for this C-axis thermal Hall conductivity, if you take a look at this green curve, you see that outside the pseudogap phase, signal was 0. However, if you go below the critical doping, which is the blue curve, so you see when you're sitting inside the pseudogap phase, and you will see a non-zero, negative, very large thermal Hall conducting signal actually coming from the phonons. So this result actually reveals a new feature regarding to the pseudogap phase is a phonon-driven thermal Hall effect that only exists below P star. And the exact mechanism behind that still remains an open question. Okay. So at this point, I want to give you guys a summary about the possible explanation for the mechanism of a phonon thermal Hall effect. So first of all, the figure I show you guys here, it was taken from Professor Campagna's group's work, which basically plotted the so-called thermal Hall conductivity versus thermal conductivity in many different types of quantum materials. So you can see that on this list, you can have either multiferroics, perichlores, frustrating magnets, and even cuprates or some other non-magnetic materials. So the main message here is you can see the phonon thermal Hall effect has been observed in more and more different types of materials. And one striking finding is actually what we found that in the majority of this material in this table, if the signal coming from phonons, one value, which is the so-called thermal Hall angle, is the ratio between thermal Hall conductivity and thermal conductivity. They always lies within a certain range, which means it's below about 0.1% to 1%. Okay, so this is like an empirical finding for these types of phonon thermal Hall effect in general. And one thing is because of all this growing list of materials, at the very beginning, people believe, okay, maybe phonon thermal Hall effect is only related to some special type of material. But nowadays, people start to think about, okay, maybe it's like a more common effects that exist for like just general insulating materials. And at this point, what people want to know is what is the mechanism actually behind the phonon thermal Hall effect. I think until today, this question still remains like open question, not fully answered. So there was still a lot of work to do on this part. So, but what I want to show you guys here is in general, the theories about the phonon thermal Hall effect, they can be loosely divided into two different categories. So one thing about the phonon thermal Hall effect, I mean, if you check the literature about 20 to 30 years ago, they will directly tell you phonon has no thermal Hall effect because phonon has no charge and no spin. So how could it couple to external magnetic field that gave you a Hall effect? So this means phonon has to couple to something else, and that thing coupled to the field that gave you a Hall effect. So in general, the theories regarding to the phonon thermal Hall effect can be divided into two different categories. The first category, we call them an intrinsic effect, which means it's based on the coupling between phonons to their pristine environment. For example, like coupling between phonons to magnons, or just general spin lattice coupling can give you a non-zero phonon thermal Hall effect. But apart from that, there was second type of phonon thermal Hall effect mechanism, which we call them an extrinsic effect. So this is related to the special scattering mechanism of phonons when they try to propagate through the material and carry heat at the same time. So for example, like what we call a skew scattering of phonons induced by impurities, defects, structural domains, or either scalar spin scalarity, some special type of Smith structure, they can all give you a non-zero phonon thermal Hall effect coming from an extrinsic point of view. So here, I just list a non-complete list of all the of some of the phonon thermal Hall effect theory that people proposed that try to explain the phonon thermal Hall effect either in cuprates, strontium titanate, antiferromagnetic insulators, or even in ruthenium trichloride. And I think on this list, I think two of our speakers today, they're going to talk about either, like Steve, he's going to talk about the phonon thermal Hall effect in alpha ruthenium trichloride. And Leo, I think he's going to talk about, introduce to us the thermal Hall effect coming from phonons, or more in general, coming from bosonic type of neutral excitations. Okay, so at this point, I mean, what I talk about or told you guys in the first part of my talk, they are all done with a magnetic field perpendicular to the sample plane. So all these measurements, we call them a conventional thermal Hall effect measurement because it just looks like an electrical Hall effect measurement. So at this point, I'm gonna move on to a new topic, which is like a new twist of measuring a thermal Hall effect, is what we call a planar thermal Hall effect study. So first of all, let me show you guys, so what do I mean when I talk about a planar thermal Hall effect measurement? So basically, this is our experimental setup. So 99% it looks exactly the same as a conventional thermal Hall effect measurement. The only difference is the direction where we apply a magnetic field. So in a planar thermal Hall effect study, we can either put the field in parallel with the heat current, or we can put the field and the current perpendicular to each other, but they are both lies within the sample plane. Okay, but for conventional thermal Hall, you put the field perpendicular to the sample plane. So the only difference is the direction where you put the field. And with this experimental setup, we were able to measure both thermal conductivity and thermal Hall conductivity simultaneously. So everything in the setup looks like exactly the same as before. And at this point, you probably want to ask me, so why do you guys do a thermal Hall effect measurement in such a weird way, in a non-conventional Hall effect configuration? Okay, so the answer is here. So actually, the very first planar thermal Hall effect study is done also in this so-called alpha ruthenium trichloride. So I think I already showed you guys this figure in the previous introduction part. So basically, for this half quantized thermal Hall conductivity reported by Professor Matsuda's group, is later on, the very first experiment was done, you can see with the configuration shows you it's done by a tilted field, which means the magnetic field had either out-of-plane component or an in-plane component. But later on, they found this half-quantized thermal Hall plateau, which is the red curve in the figure in the middle. This half-quantized plateau even exists when you put both the field and the current in parallel to each other along the so-called zigzag direction of the honeycomb lattice. So this half-quantized planar thermal Hall plateau was believed to be generated by Majorana fermions. And later on, Professor Huang's group, they tried to reproduce exactly the same planar thermal Hall effect measurement with the same configuration. They also saw a non-zero planar thermal Hall effect that shows up at a different field and different temperature. But the one thing is here, you can see there is no obvious half-quantization observed. And also their theoretical interpretation was also different, which is coming from some topological magnons or chiromagnons related to this Kitaev material. Okay, so this was the very first study of the so-called planar thermal Hall effect in an insulating material. And at this point, yes, so generally the one short summary regarding to alpha ruthenium trichloride is theoretically a planar thermal Hall effect can be generated by either Majorana fermions or by topological magnons, which is supported by theory itself. However, in real experiment, is for alpha ruthenium trichloride, this certain material, we have slightly different experimental results and also different explanations. So at this point, what we want to ask is, can other type of neutral excitations also give you a planar thermal Hall effect? How about phonons? Can we also have that? So here it goes into the result coming from our group is we actually jumping out from alpha ruthenium trichloride. We found another Kitaev candidate material, which is the so-called sodium cobalt tellurate, and also try to study the planar thermal Hall effect inside. So before I show you guys the result, the first thing I want to show is that there are several important facts about this material. First of all, this sodium cobalt tellurate, it hosts a very similar crystal structure compared to alpha ruthenium trichloride. So for alpha ruthenium trichloride, it's the ruthenium atom give you this so-called honeycomb lattice. But for this guy, it's actually the cobalt atoms forms this honeycomb lattice, which is important for the Kitaev physics. Okay. And the other thing is this material is also an insulator, and it goes into the antiferromagnetic order phase below about 27 Kelvin, which is higher than alpha ruthenium trichloride, which is only 7 Kelvin. And the last thing is the phase diagram, I mean the field versus temperature phase diagram for this material is also very similar compared to alpha symmetry chloride. So this is the data, I mean the figure that actually I took from Professor Christian Hess's group when they studied the thermal transport in this material. So here is the temperature versus field phase diagram for this material. So here they try to also apply a magnetic field inside the honeycomb plane. So you can see that when you only apply a very small magnetic field, the system still seated inside the so-called canted antiferromagnetic order phase. However, if you gradually increase the field strength, you can suppress the magnetic order and enter the so-called paramagnetic phase, or like a disorder phase, where if you have a spin liquid state, it's going to happen at this region. But if you further increase the field strength to like 12 to 14 Tesla, something like that, you will have the so-called gapped phase, which means all the spin fluctuations, they were gapped out. So this phase diagram looks exactly the same as alpha symmetry chloride. Okay. And the other thing is, what we do is we try to do a planar thermal Hall effect study on this material. But before we do that, the first thing what we can try to do is we can try to use the symmetry analysis to predict whether you can have a planar thermal Hall effect or not. So the thing is, for a planar thermal Hall effect, for example, you can measure it with a field and the heat current in parallel to each other. So this means if you want to get a transfer signal, it means your sample has to be able to tell what is left and what is right, which means this kind of mirror symmetry, or the so-called twofold rotational symmetry, has to be broken to give you this non-zero planar thermal Hall effect. And this is exactly what people already found in alpha symmetry chloride, is along the zigzag direction, twofold symmetry is broken. That's why you have a non-zero planar thermal Hall effect. However, things are a little bit weird for this sodium cobalt tellurate is if you check the global symmetry, I mean the space group of this material, you will find it holds the C2 rotational symmetry along both the A axis and also along the A star axis, which is another high symmetry axis. So in principle, you should see a zero planar thermal Hall effect because it's not allowed by symmetry. So now let me show you guys what we actually got in our result. So what we try to do here is we try to measure a planar thermal Hall effect with both the field and the current along the zigzag direction of the honeycomb plane. So the figure in the middle is the thermal conductivity versus temperature that has been taken at 4 different fields. So you can see here, 0, 5, and 10 Tesla curve, they are almost on top of each other. But the 15 Tesla curve is extremely different. So the real reason why this happened is because in this material, the thermal conductivity, they were mainly carried by phonons. And the phonons are mainly scattered by spin excitations. So when you are at 15 Tesla, you actually already entered the so-called gapped phase, which means all the spin excitations, they were gapped out. So the scattering of phonons by spin excitations, they will strongly decrease. That's why you will have a strong enhancement of the thermal conductivity at high field and only at low temperature. Okay, so actually the detailed field-dependent thermal conductivity in this material has already been studied by Professor Christian Hess's group, and we know thermal conductivity is dominated by phonons. Okay, so now let me show you what we got for the thermal Hall effect. So on the figure B here is the thermal Hall conductivity versus temperature that was taken at 3 different fields. So you can say, first of all, we got a non-zero planar thermal Hall effect for this material. And the second thing is, if you compare the panel B with panel A, you will see their temperature dependence is very similar compared to each other, especially when you compare 10 Tesla to 15 Tesla. So you see that when thermal conductivity shows a strong enhancement at the low temperature and the high field, thermal Hall conductivity shows the same thing. So this is a strong indication that whatever heat current gave you thermal conductivity should be responsible for the thermal Hall conductivity. So this is a major, kind of argument. We try to argue that this thermal Hall effect is actually dominated by phonons. Okay, so, and then next thing what we try to do is we try to apply the field and heat current to another high symmetry direction, which is the armchair direction. And again, we saw something very similar. And what I plotted here is also thermal and thermal Hall conductivity versus temperature, which shows exactly the same thing that we got when we put the field and current along A. Okay, so this is like a reproducible result along different high symmetry direction. And at this point, what we did is, okay, when we saw this non-zero planar thermal Hall effect, we thought, okay, the global symmetry tells you shouldn't have it. So what happened? So we need to do some reproducibility to check if it can be reproduced or not. So what we did next is we try to measure them in another 2 sets of samples. In total, we measured the planar thermal Hall effect in 4 different samples. And then what I plotted for you guys here is the so-called thermal Hall angle versus temperature in these 4 different samples. You can see that they show a very strong sample dependence. Okay, so one thing here is this strong sample dependence actually indicate probably the mechanism is some kind of an extrinsic mechanism because they could be linked to the sample quality of this material, like impurities, defect, dislocation, and everything. This induces this sample dependence. However, even this thermal Hall angle shows a big difference when comparing to each other. They were still very comparable to other systems where a phonon thermal Hall effect was measured, which means the thermal Hall angle lies within about 0.1% to 1%. So this is the other evidence that we usually ascribe this signal to a phonon thermal Hall effect is because of the thermal Hall angle lies within this field. Okay, so at this point, what we want to know is, okay, I only do the measurement with one single planar configuration, which is the field and the current in parallel in the sample plane. So how about we try other measurement configuration of a planar thermal Hall, which means what if we keep both the field and the current inside the sample plane, but perpendicular to each other? What will happen? Can you still have a thermal Hall effect or not? And now, in order to have a better, like quantitative comparison, what we did is we tried to do this measurement in 2 sets of sample that were actually cut from the same mother sample to reduce their, sample dependence, just to be more homogeneous comparing to each other. So what we did here is, let me use panel A and B to tell you the first set of results. So for panel A is the thermal conductivity versus temperature taken in 2 different samples. So for both of the sample, field is applied along zigzag direction, but the only difference is where the heat current was applied. So you see that when we change the heat current direction, thermal conductivity itself is more or less isotropic. It almost didn't show any change. However, what in panel B is the thermal Hall conductivity that has been taken in these 2 different configurations. You see that the red curve tells us when the field and the current is in parallel, signal is very big. However, when the field and the current is perpendicular to each other or along different high symmetry direction, the signal was strongly suppressed. Okay, and then we try to repeat the same thing, but with the field along the A star direction, which is along the other high symmetry direction, and we got exactly something very similar as the other direction. So this tells us that the thermal Hall conductivity is not 0 when the field and the current parallel to each other. However, it becomes much, much smaller when the field and the current are perpendicular to each other, but in the sample plane. And at this point, it tells us, okay, thermal Hall effect, planar thermal Hall effect, the direction of the heat current actually also matters in determining the magnitude of the so-called planar thermal Hall signal. And at this point, I want to give a very short summary about what we found so far for the planar thermal Hall effect in a Kitaev candidate material, sodium cobalt telluride. First of all, we found a non-zero planar thermal Hall effect signal with both field and current parallel to a high principal axis. And if you check the global space group, you will find along both of these 2 directions, they have a C2 rotational symmetry, which means theoretically, it should not be allowed by crystal symmetry. Okay, and the second thing is, the reason why we point it to be a phonon planar thermal Hall effect is because the thermal Hall conductivity follows exactly the same temperature dependence of the phonon-dominated thermal conductivity. So this is a very important argument for that mechanism. And after that, we tried the thermal Hall effect, planar thermal Hall effect measurement with different types of configuration, and found that, okay, you need to know the exact the correspondence direction between the field and the current to determine how large the magnitude of your planar thermal Hall effect is. And then the next finding is, so far what we found, this planar thermal Hall effect is highly sample dependent, which points to some extrinsic mechanism. And the remaining question needs to be answered is, what is the mechanism behind that? So one thing is, I mentioned, symmetry-wise, it has some kind of dilemma needs to be answered. And one thing we know, particularly regarding to this material, is this is a layered material, and it had one of the sodium layers, which is sandwiched between the Kitaev honeycomb layers, is the sodium layer is a highly disordered state. So which means you can have some local kind of disorder, and which can probably locally break the symmetry. But then the question is, can a locally break symmetry give you a global non-zero planar thermal Hall effect? We don't know yet, and we need some help from the theorists. And apart from the Kitaev materials, so I mean, starting from the planar thermal Hall effect session that I talk about here, everything I showed you guys so far was done in this so-called Kitaev material. So how about in other families of quantum materials? Can we also have a non-zero planar thermal Hall effect The answer is yes. So now I'm going to show you guys some quick slides. So basically, a planar thermal Hall effect from phonons has also been found in other types of materials, which including cuprates, which is done by our group. So we try to measure the planar thermal Hall effect in different types of cuprate materials. What I show you guys here is in particular in an electron-doped cuprate material, which is an insulating material, and we also saw a non-zero thermal Hall conductivity coming from phonon. And apart from that, my former colleague, he also studied this planar thermal Hall effect coming from phonons in another frustrated magnet system, which is the so-called Y capilla side. And we again saw a non-zero signal. So it means that this signal probably is something much more common, that is not only limited in the Kitaev system. So apart from that, not only our group and Professor Yuji Matsuda's group and the Huan's group, there are other groups try to repeat this kind of result. For example, Professor Shi Yanli's group in China, they even find a non-zero planar thermal Hall effect from phonons in some non-magnetic materials, like strontium titanate or copper oxide. So for copper oxide, people probably think that it's kind of like a more trivial type of materials, and it doesn't have all these kind of weird competing orders or magnetization inside, but still, they saw a very large signal. And apart from that, very recently, Professor Kamhambenia's group in France, they also saw this non-zero planar thermal Hall effect that are coming from another material called black phosphorus. So it's another non-magnetic type of material that hosts this very large planar thermal Hall effect signal. And the one thing nice about their study is, in my study, I only do the planar measurement along two particular directions, two particular configuration. But in his study, he was able to rotate the field inside the sample plane and to check all these kind of angle-dependent planar thermal Hall effect. So if you want to know more details, you can go into this reference. So I think they explain more on that part. Okay, so now I want to give the conclusion of my talk. So the take-home message of this tutorial session is actually very short. So first of all, the first message I want to deliver for you guys is basically a thermal Hall effect now become a very powerful probe that can be used to detect various types of excitations in many novel quantum materials. So for example, like charge carriers, electrons, quasi-particles, or some neutral quasi-particles like magnons, phonons, or something more exotic like Majorana fermions. And the kind of quantum material system that the people has already started, including unconventional superconductors, quantum spin liquids, multifluorics, perichlors, skyrmions, and even van der Waals materials. So for all of them, if you are interested in the specific type of excitations inside that can carry heat, you can use the thermal transport to study them. Okay. So the next take-home message is my focus on this talk is about this so-called phonon thermal Hall effect. So at the very beginning, people believe it's something very rare, but very recently, we start to realize it's probably a much common properties of insulators than people already believed before. And however, there still remains an open question is what is the mechanism behind the phonon thermal Hall effect? There has been various types of theories that try to explain them, but they were usually only applied to one type of materials. They cannot be like a universal theory to actually explain it. So now the question is whether there exists a universal theory to explain the phonon thermal Hall effect. We don't know. Okay. And the other message is our study is actually the first indicates the first observation of the planar thermal Hall effect coming from phonons, which actually reveal the other facet of the phonon thermal Hall effect itself is basically it can show up in both a conventional or a planar configuration. And then this probably tells you that whatever mechanism responsible for a conventional thermal Hall effect should also be responsible for the planar configuration. And the last thing, before I end my talk today, so everything I talk about to you guys, at this point, they were done in 3D bulk materials, which means all the material we measure has a millimeter size. However, on the other side of the world, basically people also tried to study 2D materials using the so-called thermal Hall effect study. For example, like some topological state in quantum Hall system in two-dimensional electron gas, or even propose to study them in twisted cuprates or in graphene, something like that. So before I end my talk, I want to show you guys one paper here. So it's from Professor Banerjee's group. They actually observed this half-integer thermal Hall conductance in some 2-deck system, which is built by gallium arsenide, aluminum gallium arsenide heterostructures. But the one thing I want to emphasize to you guys is in this kind of 2D materials, the way people do the thermal Hall effect study is very, very different as 3D people. Basically, there are two completely different techniques. For 2D material study, for this kind of thermal Hall effect, you need a very heavy nanofabrication process to first build a device for you guys. And then you need to measure thermal Hall effect that are coming from the thermal noise of the material instead of measuring the temperature directly. So if we have 2D people here and you are interested in to study the thermal Hall effect in 2D materials, you can go into this referee and all the other related reference for this related experimental setup. So yeah, I will stop here, and thank you for your attention. Leave the rest of time for questions. Thank you.